Bismillahirrahmanirrahim. Today we are going to discuss the lesson of the electric generator, which is dynamo. Let's start. Dynamo is a device that converts the kinetic energy into an electric energy. So we use Fleming right hand rule to understand its input and output. In Fleming right hand rule, we input the motion in terms of velocity in the field, so that due to variation flux lines, the field output and induced electromotive force. So the scientific idea of the device is the variation in flux lines in which the dynamo suffer variation from a vertical position to a horizontal position, and its function is to give the dynamo kinetic energy, as we can see, and this causes motion for rotating coils or magnets with respect to each other, such as to produce an induced electromotive force. As we can see here, we give this rotating wheels turbine, which is turbine a push, and it makes the coils to causes the coil to rotate. Okay, let's move on to the shape of the coil during rotation. We have here the transversal sides, which makes no output as they are given the motion parallel to the field, while the longitudinal sides, which are the active sides that outputs the electromotive force, since they are given the motion perpendicular to the electric field. So the transversal sides has no output, since they are given the motion parallel to the electric field. We have here two longitudinal sides, and that's why electromotive force is equal to 2 belv sine theta, and we have to make LV equal omega r, as we know. So we replace LV, we substitute for omega r. Therefore A electromotive force equal 2BL omega r in the place of V sine theta. And as we know that length times width equal areal width, the width here is equal to the diameter. Width here is equal to the diameter of rotation. So we substitute A for L to R in the deduction, and we have in turn the final formula is going to be electromotive force instantaneous during rotation equal nabo sine theta. And we have to distinguish between the positions, the perpendicular positions and the parallel positions and the inclined position. In the perpendicular position or vertical positions, we find that the coil area is perpendicular to the field, while the motion of the coil is parallel at the same time. This is because we have two active sides are given the motion, and we simplify the motion by replacing the two directions with the normal direction to the coil rotation. So the velocity here is one direction normal to the plane of the coil, normal to, and here the motion or the velocity is parallel to the field and no output as we substitute LV parallel B parallel to B, so angle here is equal 0 and the output of course sine 0 multiplied by these factors equal 0. On the other hand, the parallel will output maximum value when we can see that the normal to the coil, which is the velocity, is perpendicular to the field. While in the inclined position, we have to know that the angle of inclination between the velocity direction and the field, it is equal in substitution to the angle of rotation from a normal position. So if we select the vertical position as a start position to change with time using the sine graph, we have to know that the angle of rotation from a normal position, I mean that the coil in its start position is applicable to the normal to the field, and it makes an angle theta with respect to it, with respect to the normal to the field. In such a case, the angle of rotation from the normal position is equivalent in substitution the angle of the direction between the direction velocity and the field. Of course, the direction of velocity is the normal to the plane of the coil. And that's all for now. Thank you.